Welcome to this college algebra video about common logs, natural logs, and some applications. First of all, let's define what the common log is. We know that logs can have different bases. Well, the log with base 10 is also referred to as the common log because it is used in so many situations. So when we write log base 10 of x, we can actually omit the 10 and just write log of x. It's understood there that the base is 10. Another log that we find used quite often is called the natural log. A natural log is a logarithm with the base e. Remember the constant e that we talked about a few sections ago when we talked about continuous compounding. The log base e of x can be written ln of x. These two logs are used so often that they actually usually have their own button on a calculator. Use the LOG button for the log base 10. Use the LN button for the log base E. In this lesson, we're going to see how to both use the log button and the LN button, and then how to solve a log equation. We're going to use a strategy of raising both sides of the equation as a power of the base. The log button on a graphing calculator, such as the TI-84, is pretty easy to use. We just look down the left-hand side, find the button that says log, and type in the argument is what we call it. So log of 825.8 is equal to 2.91687. Now, usually when you are evaluating a log, you'll have some kind of accuracy that's asked for. In this case, we're going to express each answer to 4 decimal places. So we'll write 2.916 and round up to 9. For the next example, let's do the log of 0.00069. We get negative 3.61, and then I'll round the next digit up to 2. And notice that this answer is negative. Some logs are positive, some logs are negative. The cutoff point is log of 1. Remember that log of 1 is always equal to 0 because any number to the 0 power is 1. So for any number greater than 1, the log of that number will be positive. For any number below 1, the log of that number will be negative. The natural log of a number is just as easy to find. Let's find the natural log of 79.5. Natural log of 79.5 is 4.375, and I'll round that next digit up to 8. And finally, natural log of 0.008142. Now, since we're taking the natural log of a number that's less than 1, we should expect to get a negative answer, and that is indeed what we get, negative 4.810, and I'll keep that last digit a 7. Next, I'd like to illustrate a method for solving a log equation. When we have log of x equals a number, we can raise both sides of this equation as a power of the same number. Now, the smart number to choose would be the base of this log. So we're going to raise both sides as a power of 10. What we've done is, in a sense, we have taken that log expression and rewritten it in an exponential form, similar to an idea that we saw when we first introduced logs. Now we'll take a calculator and find 10 to the power 1.5263, and our solution is that x is equal to 33.5969637 approximately, and this time our directions are to express the answer to 5 significant digits. So we'll take the 33 and then 3 digits after the decimal. That will be 33.597. The equation below it will be solved in a similar way. Raise both sides as a power of the base. The base of the common log is 10. So x is now equal to 10 to the negative 0.1452. When we use this technique, we can almost think of the 10 and the log as canceling each other out. They are inverse operations, 10 to a power and log base 10, so they essentially cancel each other out, leaving behind just x. And 10 to the power negative 0.145 is 0.71614. And I'll stop at the 4 since that gives me 5 significant digits. Now every log equation cannot be solved by raising as a power of 10. What we have to do is pay attention to the base. The base of our log is the number we want to use. And remember that natural log is another way of writing the log base e. So I'll raise both sides of this equation as a power of e. E will essentially cancel out the natural log. E to a power and natural log are inverse operations, and this leaves just the variable x. Now on a calculator, I'll do e to the negative 2.3745. Now on most calculators, e is associated with the same button that you see natural log. And in this case, we hit second natural log, and we start getting an exponential function with a base e. We have e, and we're going to raise it to the power negative 2.3745. We get a result of 0.09306. We'll use the 1 to wrap up our 5 significant digits. The 0 before this 9 does not count as one of our significant digits. For this last example, we're again going to remember that the base of natural log is the number e. So we'll raise both sides as a power of e. E and natural log will cancel each other out, leaving behind just an x. And on a calculator, we'll see what e to the 3.0259 is. Hit second natural log to get the expression e to a power. Type in 3.0259 for our power, and our result is 20.6125. To get 3 significant digits, we'll say 20.613. Let's look at some real-world examples where common log and natural log come into play. You've probably heard of a pH scale, either in a chemistry class or maybe when talking to somebody about a swimming pool. Well, pH values are measured on a logarithmic scale, meaning that every time we move 1 unit up along the scale, we're actually getting 10 times the concentration. pH measurements typically range from 1 to 14. To calculate a pH value, we're going to take the negative log of the hydronium ion concentration. So let's use the formula and find the pH of a solution where H3O plus has a value of 2.5 times 10 to the negative 4th. We'll do the following calculation. pH is equal to negative log of the number 2.5 times 10 to the negative 4th power. The calculator will come in handy here. Hit the negative button at the bottom. Log of 2.5 times 10 to the power negative 4. We get a pH value of approximately 3.6. For question B, we're actually trying to solve for the hydronium ion concentration. To solve this equation, first we'll divide both sides by negative 1. So negative 7.1 is equal to the log of x. And then to solve the log equation, we're going to raise both sides as a power of the base, which is 10. This is the common log. Raise both sides as a power of 10 to cancel out the log. On the calculator, I'll do 10 to the power negative 7.1. The result is a very small number. This is a number written in scientific notation, but don't use the calculator's version of scientific notation. Let's translate it into actual scientific notation. We'll write that x equals 7.9 times 10 to the negative 8th power. Another situation that uses a logarithmic scale is the decibel scale. Each time the decibel rating goes up by 1, the actual intensity of the sound is increasing times 10. For decibels, we refer to I sub 0, which is the intensity of a very faint threshold sound, a sound that is barely able to be heard. This problem asks us to find the decibel rating, D, of a sound with intensity 10,000 times I sub 0. Well, we'll set up the formula D is equal to 10 times log of I, which in this case, the intensity is 10,000 times I0, divided by I0. When we cancel out the I0 in the numerator and denominator, that means that we're going to do the calculation 10 times log of 10,000. We can get a calculator out and do this calculation, 10 times log of 10,000, and find a decibel rating of 40. The last application comes from geology. Potassium 40 is an element found in rocks. Potassium 40 is slightly radioactive and decays into a different element called argon 40. By measuring the ratio of argon and potassium, it's actually possible to find the age of a rock. Now, don't worry about that complicated formula. We're going to let the calculator do most of the work. In part A, we are asking how old is a rock in which the value of A equals 0 and K is greater than 0. By the way, K is the atomic symbol for potassium. So what we're saying here is that there is some amount of potassium in the rock, but there is no argon. Now, if we think about this logically, that means none of the potassium has decayed into argon. So that should mean that no time has passed at all. This is basically a brand new rock, maybe formed by a volcano. If we put the numbers in the formula, we're going to say that T is equal to 1.26 times 10 to the ninth power times the fraction natural log of 1 plus 8.33 times the fraction 0 over some positive number. That fraction would just equal 0. All this divided by natural log of 2. When we do this calculation on a calculator, we can indeed confirm that the answer is 0. This is because this numerator works out to natural log of 1, which is a value of 0. So this rock is essentially brand new, T equals 0. Let's do the same calculation, but this time the ratio of A over K is given as 0.212. In our formula for T, most of this stays the same. We still have 1.26 times 10 to the ninth power. We're going to multiply times the fraction ln of 1 plus 8.33, and here's where we make a change. The ratio is now 0.212. We'll still divide by natural log of 2. Going back to our calculator, we're only going to change the value of A over K. So we're going to change the 0 to 0.212. And the calculator gives us a value of 1849403,169. Or to put it another way, 1,849,403,169 years old. Now, of course, this is just an estimate, so we would probably say that this rock is approximately 1.8 billion years old. Finally, we're going to talk about something called the change of base formula. This is a formula that allows us to calculate logs of other bases if all that is available to us is the log button or the natural log button. Here's the general form of the change of base formula. To find a log other than base 10 or base E, we can use this change of base formula. The log base A of X is equal to the log base B of X over the log base B of A. So this is a way to change from one kind of a base, A, to a different kind of base, B. On a calculator, the logs that we have available to us are usually the log base 10 and the log base E. So we'll usually either use this formula as log of X over log of A, or natural log of X over natural log of A. In a previous video, I've already shown you how to dig through the menus of a graphing calculator to find log base A in the math menu, but this time I'll show you how to do log base 7 of 20 using just the buttons on your calculator. So we're going to translate this using the change of base formula into log of 20 over log of 7. We put log of the 7 in our denominator. We'll calculate this directly using just the buttons on the face of our calculator. Put log of 20, be sure you close parentheses, divided by log of 7, close parentheses. And we find that log base 7 of 20 is about 1.5395. Notice that we would have gotten the same answer if we had used the natural log button. Natural log of 20 divided by natural log of 7 gives us the same value. For comparison's sake, remember that we can go through the math menu and dig down deep into here until we find the log base option. And again, that value comes out the same. So this gives us 3 different options for finding a log which has a different base than 10 or E. To find log base 11 of 350, we'll either need to stick with the log button or stick with the natural log button, your choice. The calculator tells me that natural log of 350, close parentheses, divided by natural log of 11 is approximately 2.4429. So hopefully this section has given you a good idea of how to use the log button and the natural log button on the front of your calculator to solve problems. Thank you for watching this video, and we'll see you next time.